Great.
Well, howdy, friends. Welcome back. Welcome back. We are going to continue with topic number 9, which is troubleshooting series parallel circuits. This is part B, and we're going to get into circuit design, circuit analysis, circuit troubleshooting with some new tools. So, with that being said, let's go ahead and jump into this. Oh, by the way, these videos are intended for self-study at home, or they can also be intended for supplementing the lab experiments that you may have with your instructor in college, either in an electronics engineering class or an electronics technology class. And for some high schools, perhaps the electronics portion of their physics courses. So let's jump into this. We have some fun things to talk about. All right. First thing I want to show you is the difference between open loop versus closed loop schematics. In prior training videos, went through 8, you've been shown closed loop circuits, and closed loop circuits are shown in the right side, excuse me, left side of the slide. And this illustrates the path for electron current flow as it leaves the negative plate of the voltage source, flows down, and it makes a right turn at the bottom, and then makes a turn going up through R3 and then R2 and then R1, and making a turn back to the positive side of the source. So electron current model is designed to flow in this fashion. The ground is shown only as a reference point. There is no electricity flowing to ground, unlike what you may experience with electrical circuits at home or in industry. So take a look at what I've drawn as the open loop circuit. And as the open loop circuit, instead of the one ground and a wire loop, I have 2 separate grounds. At the bottom of the voltage source, there is a ground symbol. At the bottom of R3, there is a ground symbol. And so with open loop schematics are far more common for advanced circuits, as the connection between the grounds with a wire is not needed on the schematics. Multiple grounds, as many grounds as there may be shown, are all connected virtually to each other. They are all 0-volt reference points, and the electron current flow will flow normally. When you see the next few diagrams, you'll see how this is going to be possible. But I wanted to show you open loop versus closed loop. So moving on with more examples of open loop, take a look at this. All right, so here's an advanced circuit. This happens to be a summing op-amp circuit, something you will probably see in the next semester. And what it is that we have here, if you take a look, I've got 8 ground symbols. There's 8 of them. There's 4 on the left-hand side, there's a 3 in the middle, and then 1 on the far right-hand side underneath the looks like a multimeter. And they are all interconnected virtually. There's no need to draw a wire between them. So it makes for a cleaner display of your schematics as they become more and more advanced. Next, the 2 major troubleshooting tools that you'll be using in this exercise will be called nodal analysis. You should write that down in your journal. Nodal, N-O-D-A-L, analysis. Speak that out. Write that down. And then also current analysis. They are related, but they are distinctly different. If you take a look on the left-hand side, nodal analysis analyzes the currents entering and exiting the nodes. So I happen to have in the drawing a big blue node. And so the rule for nodal analysis is stated this way. The rule says that the sum of currents entering any node must equal the sum of currents exiting that node. So all the currents that come in, however we sum them up, the inbound currents must equal the sum of all the outbound currents. And so with the illustration that I've shown here, and I'll explain this in greater detail, later on in this training video, is you are shown 3 outbound currents in red, you're shown 2 green inbound currents, and your task is to figure out the yellow path. Is that going to be inbound or is that going to be outbound? And not only is it going to be in or out, what value is that current going to be in that yellow path marked X? Okay, so we'll talk about more of the solution of this. It's a very easy method, and I'll show you that later. Now, the other very powerful troubleshooting tool that you'll be introduced to in detail in this training video is called current analysis. And current analysis tracks the movement as well as the values of currents as they flow through the circuit. So in the yellow, I've stated using electron current, we can see how the electron current leaves the voltage source downwards to ground symbol and travels through the series parallel circuit back to the voltage source. And this illustration will be explained in greater detail in the next portions of our training video. But I wanted to show you a visual that shows the current paths that will allow us to do the current analysis of how the currents flow around in a series parallel. All right, now we'll talk about a loaded versus an unloaded voltage divider. You've played with voltage dividers before. I've shown this to you in the series circuit training video, as well as the troubleshooting of the series circuit video. So briefly, to redefine, unloaded voltage divider is simply, on the left, a basic series circuit with either 2, 3, or more resistors serving as the basic loads. Now, I've defined at the bottom of the slide what is a load. I've used that word, loaded versus unload, and resistors as being basic loads. So the definition for a load at the bottom in yellow, a load is any device in an electrical circuit, such as a resistor can be a load, an LED can be a load, a fan can be a load, a potentiometer can be a load, a siren, a bell, a refrigerator, an AC unit. They are all loads if they are attached to an electrical circuit. And you may have heard of your local utility being very concerned during very, very hot days of overloading the circuits in a municipality. So the loads on a electrical circuit in your municipality that may be in danger of overloading would certainly be the air conditioning circuits. So we will simply look at loads in our studies for now as being resistors. So the voltage divider on the left has 3 loads, R1, R2, R3. It is a simple series circuit, and I've drawn this as an open loop circuit, not as a closed loop circuit, so you can get used to looking at open loop circuits more and more. A loaded voltage divider is more practical. See, the unloaded one on the left is what we use to introduce the concept of Ohm's law, how current flows in the circuit, how to do your calculations. But a practical application of a voltage divider is shown on the right. And that is we're going to load the voltage divider. It becomes then a parallel circuit, a series parallel circuit. This is where we are going to attach separate additional loads, additional resistances to this circuit. And as you can see, we are attaching a resistor number 4 and a resistor number 5. And where we attach them is very specific. And also the loaded voltage divider, the additional loads, may have very specific voltage and current requirements. They may require very specific needs. R4, as you can see there, as it's attached to the voltage divider, may have a voltage requirement and a current requirement. Same thing with R5. So let's explore this a little further. Here you are asked to design. Hey, we're graduating beyond just looking at Ohm's law and doing calculations. We'll continue with calculations, but now with a bit more purpose. So You're asked to design, you're asked to come up with an unloaded voltage divider. So basically, what is an unloaded voltage divider? We defined it as a simple series circuit with either 2 or 3 or more resistors as loads. That's how we defined it in the previous slide. The circuit requirements for this particular unloaded voltage divider specifies, given 3 resistors, 1 voltage source, in the illustration shown on the left, there will be a point A above R1, there will be a point B between R1 and R2, there will be a point C between our resistor 2 and 3, and there will be a point D at ground. So your task is to, and we've done technician point voltage to ground analysis before. We've done this in voltage divider series circuits analysis in a previous video. So you should be able to understand what V sub A, subscript A means. V A means the voltage at point A measured what? Measured with respect to ground. Red probe at A, black probe at ground. It is required that it must be 5 volts. Then take a look at voltage B. Voltage B means the red probe is at point B, black probe is at ground. How much are we going to need there? The design parameters require 4 volts at point B to ground. Point C, voltage at C, is voltage at point C with respect to ground. Remember, we use these terms a lot, with respect to. And that means the red probe will go to point C and the black probe will be at D, ground. And what do we expect between those two? The requirement says we have to have 2 volts there. And then the voltage at point D is specified because it is at ground, going to be 0 volts. Now, those are the design requirements. Your task is to build a series circuit shown on the right, and using 3 resistors in order to achieve the required voltages at each technician test point with respect to ground. And I have on the breadboard illustration a point A, a point B, a point C, and a point D. A is at the top of the string of resistors. Point B is between R1 and R2. Point C is between R2 and R3. Point D is at ground, which is hooked up to my negative rail. So how are you going to figure out what 3 resistors you can set up in order to achieve this? Now, don't bother trying to read the resistor color bands. It's a little hard to discern in the photograph. I've tried to bring out as much color as possible, but really try to figure this out using the noodles between your ears. You can do this. I'm giving you a hint. Before you can figure out the resistor values, you first should determine the voltage VR1, VR2, and VR3. In other words, first of all, determine how much voltage is going to be across R1. You are already given the point voltages, the technician test point voltages with respect to ground. The hint is, can you figure out what each resistor will drop? What is the voltage across R1 by itself? What is the voltage across R2 by itself? What is the voltage across R3 by itself? So think about this. I've got a stop sign here, and that is for you to click pause and give this some thought and look over the notes that you've accumulated so far from the beginning of the first slide of this training video, as well as what you've accumulated in previous training videos in your journal, as I've suggested all along. So you put this on pause, and we'll come back after your pause. Okay, coming back after our pause, hopefully you remember this way back in an earlier training video. You were introduced to the electrical units table. And the electrical units table, this is just a portion of it, shows a symbol for the quantity. So this capital V is the symbol for the quantity we call voltage. The units of voltage are called volts, and the symbol for volts is also a capital V. But I show you this to reiterate the brief descriptions that are shown in the chart. In particular, you should remember one definition. Voltage is defined as the pressure to move electricity. More pressure means more electricity can be moved. Number two, voltage is also defined as electromotive force, the force that actually moves the electrons in the circuit. Number three is the one we're going to emphasize for the solution here. And voltage is also defined as the difference of charge or difference of voltage between 2 points. It's always, always, always going to be between 2 points. So let's take a look at this reminder. The reminder says one definition of voltage is the difference of charge between 2 points. Now, difference means what kind of math? If sum means to add, what does difference mean? Yes, difference means to subtract. So if you take a look at us trying to determine what VR1 is, VR1, the voltage across R1, is the voltage between point A and point B. We looked at multi-point voltages in a previous training video. So when you see V subscript AB, that means the first letter gets the red probe, the second letter gets the black probe. Is there potential at point A? Point A is clearly stated as 5 volts with respect to ground. Is there potential at point B? Point B is clearly stated as 4 volts with respect to ground. Is there a difference between point A and point B? Do the math. VA subtract VB is equal to 5 volts, subtract 4 volts. That's equal 1 volt. That's highlighted in yellow. And by the same token, take a look at VR2. VR2 is the same as the voltage between points B and C. Is there potential at B? Is there potential at C? Let's take a look. Potential at B is 4 volts. Potential at C is 2 volts. What is the difference of potential? The difference of potential is voltage B minus voltage C, which in this case is 4 volts minus 2 volts, because those were the requirements of the design. So what's 4 minus 2 is 2 volts. Lastly, voltage across R3. R3 exists here between point C and point D. Is there a difference between point C and point D? Yeah, point C has 2 volts, point D has 0 volts. Let's do the math. Voltage C subtract voltage D is equal to 2 volts minus 0 volts, and that's also equal to 2 volts, and I've got that bolded in yellow. So here's a double check for you. In a much earlier training video, we discussed series circuits. And what do you remember of one of the rules of series circuits? In series circuits, the voltage across R1 added to the voltage across R2, added to the voltage across R3 in series must add up to the voltage source. Well, your design parameter specified the voltage source as 5 volts. We just calculated 1, 2, and 2. So does VR1 add with VR2, add with VR3 to give us the voltage source of 5 volts? Yes, it does. Isn't that cool? All right. That was the hint. We had to calculate the voltages across each of the resistors first before we can have any hope of determining the value of R1, R2, and R3. So what's the next step? Let's take a look. Next step. Have you thought about the values of R2, 1, 2, and 3 yet? Maybe, maybe not. Here's a hint. And the hint here is to recall VDF. And VDF stands for voltage divider formula. And it is given to you in the formula in the white box, where VRX, X meaning some unknown resistor, is equal to the value of a fraction, a ratio, a proportion of Rx over R total. You take that fraction, you multiply it by the total voltage or the voltage source, then we can determine what part of the voltage source is going to be equal to the voltage across Rx. So it's like, what part of the pizza pie are you going to get? If that fraction, Rx over RT, if that fraction represents a fraction of 1 over 2, what's 1 over 2? Half, right? And if VS represents the whole pizza pie, and you're going to get half of the pizza pie, then your calculation for VRX would be 1/2 of whatever the voltage source works out to be. It's the best analogy I can give you. So further hint, isn't VR1 over VRT, isn't that ratio proportional to R1 over RT? See, we're substituting VRX with an VR1, and we're substituting an RX with R1. So there's a proof. Some people say, oh yeah, I'm not going to take your word for it. Prove it to me. All right, we're going to prove it to you. And let me get my mouse back over here. All right, with a little bit of math, with a wee bit of math, this is what we're going to do. Not hard, trust me. We look at the original voltage divider formula. I gave it to you in the previous slide. VRX is equal to the ratio of RX over RT times the voltage source. What are we going to do? Follow the red arrow. We're going to move VS to the other side of the equation. How do I move VS? That's going to be multiplied by this fraction. How do I move this to the other side? Well, the movement is called transposition. And I'm going to move this to the other side by using the opposite math. So on this side of the equation, VS is being multiplied. When I move VS to the other side, what is the opposite of multiply? It's going to be divide. So when I move VS to the left side of the equation, it becomes VS is going to be divided into VRX. So I now have two fractions, VRX over VS, the voltage source. So the voltage over the unknown resistor over the voltage source is equal to the original fraction that we had of RX over RT. Then what we're going to do, come down, we're going to replace the VRX with the VR1. So we're going to look specifically not at R1, R2, R3, Rx, but specifically at the voltage across R1. In order for us to do this, we have to replace the Rx in the formula with R1. So VR1 over the voltage source is equal to R1 over R total. Next, follow the red arrows. We're going to come over here, leftwards. And what you're going to see is we're going to replace VR1 and VS with something very simple. Well, we stated that voltage source is going to be 5 volts, and the VR1 we calculated in the previous page was 1 volt. So 1 volt over 5 volt is the ratio that we get when we use our calculated voltage across R1 across the total of 5 volts. That must equal to the other side, to the resistor side. So if I have 1 volt over 5 volts, that's the same as must be 1 ohm over 5 ohms. This starts to reveal to us what kind of resistors we can come up with in order to build this unloaded voltage divider. So think. Which resistors in your kit can you build for a 1 ohm to 5 ohm ratio? Give it some thought. We can't quite figure it out just yet. You need more hints. You need more tools. So let's go on to the next part that will help you figure this out. Okay, with a wee bit more math, this is what we're going to do. Take a look at the upper left. We have a ratio, VR1 to R1 ratios. So VR1 was 1 volt, R1 was 1 ohm. If we take a look at VR2 to R2 ratios, the voltage we calculated previously for R2 was 2 volts. Well, 2 over 5 must equal to 2 over 5 on the right-hand side, resistor side of the equation, so we have our numbers there. VR3 we calculated also is 2 volts. So if we pop VR3 of 2 volts into this ratio, what's 2 over 5 on the left-hand side must equal to 2 over 5 on the right-hand side. That's what an equation is. So take a look at the narration on the left-hand side of the screen. Since you do not have 1 ohm resistors in your kit? You don't have them unless you special purchase them in a separate package, as I've shown you before. You don't have 1 ohm resistors in your kit to build 3 resistors totaling 5 ohms. So what other combinations of 3 resistors in your kit will closely satisfy the resistor ratios without using potentiometers? We went through an extensive discussion about potentiometers in a previous training video, but we're not going to use potentiometers in this case. But if you hadn't visited the previous training videos, you're wondering what is the KOGUY talking about potentiometers, look up a previous training video of mine. All right, so we're going to build 3 resistors that must satisfy these ratios. How are we going to do this? Which resistors in your kit can you build for these ratios? All right, you noodle it out with that wonderful gray stuff between the ears, and lo and behold, you guessed it. Yes, ta-da. Since the VR1 to VR total ratio is proportional to R1 over R total ratio from your kit, perhaps you can try, and you have these in your kit. Let's try R1 being 1 k ohm. Let's try R2 being 2 k ohms. Let's try R3 being 3 k ohms. If I have 1 k ohm in series with 2 k ohm in series with 2 k ohm, does my R total equal 5 k ohms? Hey, isn't that cool? Does this then satisfy the ratio that we're looking for of 1 to 5 for R1? R1 is 1k over 5k. That satisfies our 1 to 5 ratio. How about with R2 being 2k and the total being 5k? Does the R2 over RT ratio and R3 over RT ratios, do they satisfy the 2 over 5? Yes, they do. So since you have them in your kit, you can now build this into the breadboard, and we're going to hook up R1 in sequence with R2, in sequence with R3. We're going to label point A, point B, point C, point D. Point D is attached to the negative side of the voltage source, and I have this brown jumper wire doing this. Point A is attached to the positive side of the voltage source, and I have the orange wire jumping to the red rail. Cool. So with that being said, what do we need to do at this point in order to complete our design of the voltage divider, the unloaded voltage divider? Here we go. You just need to fill in these values. You're going to build this. You're going to measure this. You're going to measure the ohms of R1, ohms of R2, ohms of R3. You got to make sure you have the right resistors pulled out and built on the board. You got to measure them to make sure the right resistor is in the right place. You don't want the 1 k ohm where you're supposed to have a 2 k ohm resistor. You don't want them flip-flopped. So you got to measure the ohms, make sure they're in the right place. Let me pause this, sorry. All right, sorry about that, friends. I needed to have the phone in something other than silent because it's a very important call I'm expecting. Anyway, that's over and done with. So back to the slide that's in front of us. You need to measure individual resistances, measure total resistance, make sure the resistors are in the right place, and you want to measure the voltage across R1, across R2, across R3. Do they match with your calculations? Okay. And then you're going to measure voltage at point A, point B, point C, and point D. Do those voltages, the technician test point voltages, do they match with your circuit requirements of your design? So best thing to do is to make sure in your journal at this moment, you see the stop sign, put this on pause. If you haven't already copied the schematic down in your journal and copied down these blanks to be filled in, do so now, because in a moment, when we come back, we're going to go to the camera mode and then do these measurements and fill in these values, okay? So I'm going to put this on pause, and we'll go to camera mode. Okay, we're now in camera mode and I've got my multimeter set up, turned on, backlit, and it's got to be on continuity because again, every time before we do any measurements with the probes, you want to make sure that the probes are properly connected and they are working properly. So we're going to do what's called the continuity test. When I go to tap these two probes together, you should see in this particular multimeter, this should go to something close to 0 ohms. And there also happens to be an LED that lights up there. And there's also a beep, which the microphone may or may not pick up. But let's go ahead and test this. 0 ohms, the LED lit up, and I can hear the beep. Release. All right. That means the probes are working. Now we're going to test for resistance. Resistance was our first task. And so if you recall, you cannot measure resistances with the power supply that's on the board. So you have to disconnect the power supply, and we can do that either physically or we can just remove a jumper. I'm just going to remove a jumper. I'm going to take this, yank this out, and just park it. Okay, now it's parked. Oops, come back here. And park. Okay, now it's parked. And so the power supply is still on the board. It's not energized, but because I don't have a return path at the bottom of the resistor to the negative side of the power supply, I do not have a connection back to the power supply. So now the circuit is independent and a happy camper. So I'm going to go and measure. This should be a nice 1 kilo ohm. And it doesn't matter if you recall with the resistor, which polarity we use for resistors, because resistors are not polarized. That's a nice 1K ohm resistor. Let's go to point B to point C. We hope to see 2K ohms or something close to it. Yes, we do. These are 1% precision resistors, so pretty good. And the last one hopefully should also be another 2 kilo ohms. And that's what I measure. So whatever you measure at this moment, along with me, you pause this as you need, you make the measurement, you need to record your values into your journal. And the thing about measurements is you record everything that's on the display. You don't round anything on the display. Unlike your calculator, you're rounding to the hundredth. With a measurement, you record the actual value. That's just good lab technique. And then here, we would record an actual 2.008 kilo ohms. So it's 2008 ohms is what that works out to be. And here we will record an actual 2.00, hold steady, 5. We'll call it 2.005 kilo ohms. And if this is built properly across all of them, we should have 5 kilo ohms, something close to it. Let's see what we get. Hey, look at that, 5.00 k ohms. Pretty sweet. Okay, next, after filling in your resistance measurements, we're now next going to go to measuring our voltages. So I need to pop the jumper back, and we will go ahead and switch this to voltage mode and then now energize the circuit. And as we energize the circuit, we expected to see voltage across R1 as being something close to 1 volt. All right, so I have this on volts, I have this on DC volts, and the reason why this display is flickering here in the millivolt range to microvolt range is because the wires of my leads are acting like antennae, and they're picking up stray radio frequency waves that are flying around. But here, let's go ahead and measure this and see what we've got. And let's take a look here, across here. It's right at, push this back down, make sure everything is nice and stable there. My voltage across R3, 2.07 volts. Voltage across R2, supposed to be something close to 2 volts, and it is 2.0, come on, hold steady, 2.06 volts. And here's something close to 1 volt, I get 1.023 volts. So you record that down. So we have basically 1 volt across R1 and basically 2 volts. Well, just keep squishing these wires. Okay, 2 volts across R2, and basically we should have about 2 volts across R3. So our voltage divider is built properly for the ohms being in the right places, and the voltages across the resistors being correct. Now we're going to go make the measurements of our technician point voltages with respect to ground. So I will hold the red probe here and the black probe at ground, and we expected something close to 5. Now my power supply is a little beefier than 5, so I'm going to get something more than 5. And a little shaking in my hands is never a good thing, but let's go ahead, hold steady. There, we got a nice more than 5 volts. And we want at point B something close to 4. We get something close to 4, record what that value works out to be. And then at point C, something close to 2, and we get something pretty close to 2. So 2 volts at point C, 4 volts at point B, and something in this particular power supply, something in excess of 5 volts at the top. Okay, cool. So that as you've done your measurements alongside of mine, we want to record those values into your journal, and then we'll move on to the next challenge. Come on, mouse. Where is my mouse? Mouse. And all right, so our task was to fill in this particular slide with the necessary values from your measurements. And in doing so, I've done my values into here. And I have shown, as I've discussed before, if your digital multimeter has the resolution to show you all the digits after the decimal point, record all the digits as you see off of your digital multimeter display. So R1, R2, and R3, yeah, very close to the desired 1K, 2K, and 2K. The total, very close to the desired 5 kilo ohms. The VR1, VR2, VR3, we calculated approximately 1 volt, approximately 2 volts, approximately 2 volts, and that's what we got for VR1, VR2, and VR3. The requirements for test point voltages with respect to ground, your technician test point voltages, VA was supposed to be 5. Well, mine's a little beefier than 5, so that's where it ended up. Voltage at point B, something close to 4 volts. This is pretty close to 4 volts. Voltage at point C, something close to 2 volts. It is. And voltage at point D is should be 0, and it is. You put the red and the black probe at the same point, you're going to get a 0. So hey, congratulations. Pat yourself on the back. Give yourself an applause. You know, an attaboy, attagirl. This is great. Your design matched the design required parameters. It was required that you build 3 resistors. It was required that point A, B, C, and D were 5, 4, 2, and 0 volts. And you have achieved that with everything that we've done with these slides at this point. Now, where do we go from here? Here's where the stuff gets really good, because take a look at this. That we're going to design a loaded voltage divider. So this is something, as I've said, that's quite a bit more practical and useful. Is voltage dividers by themselves are simple learning tools, but a loaded voltage divider is far more interesting because it shows the practicality of us attaching a load, in this case R4, attaching another load, in this case R5, and we're going to attach the loads to the voltage divider at very specific points. R4 will be attached to point C. The other side of R4 is at ground. R5 is going to be attached at point B. The other side of R5 will be at ground. So the circuit requirements have not changed. We have to maintain the original circuit requirements of 5 volt source, 5 volts at point A, 5 volts at point 5 volts at point A with respect to ground, 4 volts at point B with respect to ground, 2 volts at point C with respect to ground, and 0 volts at point D. But take a look at the requirements in yellow. It says VR4, when it's attached to point C, requires 2 volts and it requires 1 milliamp flowing. That's just a flat out design requirement. And the design requirement is specified by your instructor or specified in a test situation. R5, on the other hand, is something that requires 4 volts with a 1 amp milliamp flow, with a 1 milliamp flow of current. And so how are we going to achieve this? Well, we can do some basic Ohm's law right now, because if you take a look at R4, R4 is attached to point C. R4 requires 2 volts and it has 1 milliamp. So you have the voltage, you have the current. Your task is to calculate the resistance. Back to Ohm's law. R is equal to something. Do you remember Ohm's law? Go back to your journal, look it up. How do you calculate resistance when you are given a 2 volt source and a 1 milliamp current flow? By the same token, R5. How can we calculate the value of R5? Well, according to Ohm's law, the value of resistance of R5 is equal to the voltage of R5, in this case 4 volts, divided by the current through R5, which in this case is specified as 1 milliamp. So what does this look like? It looks like this. Here we go. From the load requirements and Ohm's law, you can now calculate the value of R4 and R5. R4 is VR4 of the 2 volts divided by 1 milliamp. That gives you 2 k ohms. R5 is the voltage across R5, which is 4 volts, divided by the current through R5, which was required at 1 milliamp. So what's 4 volt divided by 1 milliamp? That's equal to 4 kilo ohms. So there you go. Now you know you've been able to calculate 2 k ohms for R4 and 4 k ohms for R5. And as a point of reminder, let's just go ahead and do this on our calculators, because don't just look at my screen, listen to me talk. You need to do the calculations. You need to verify this. So you put this on pause. So using our prefix calculator, what it is we're going to calculate is 2 volts divided by 1 milliamp. So that is clear. We're going to enter the 2 and divide by, and 1 milliamp is keyed in as 1 shift. The milli key is this one here, and you can see on the display I've got 2 volts divided by 1 milli. If I hit equals, I immediately get 2 kilo. Okay, 2 kilo. Now I can do the same calculation without the prefixes. If you don't happen to have a prefix calculator, it would be done this way. It would be 2 divided by 1, and the way you key in milli on a non-prefix calculator would be EXP and then change sign 3, because that will give you milli. So it's 1 milliamp. So 2 volts divided by 1 milliamp, hit enter. And what this shows you here in the prefix calculator, you get 2 kilo. On a non-prefix calculator, you see 2 power 10 power 3. Okay. All right. Let's do the other calculation. The other calculation will be 4 divided by 1 shift milli, and that equals 4 kilo ohms. Okay. All right. Cool. So yes, we calculated R4 as being 2 kilo ohms, R5 as being 4 kilo ohms. That's just straight Ohm's law math. Pretty straightforward, and we verified that with our calculators. So now let's take a look and see what's next. It says, so are we done? If we build this circuit with all the calculated resistors, the answer is nope, we're not done. There's going to be some kind of a challenge here. If we keep these resistor values, R1, R2, and R3 of 1 kilo ohm, 2 kilo ohm, 2 kilo ohm respectively were needed of those values in those places to achieve the voltages that were required as the design. Once we loaded the voltage divider with R4 and R5 attached to point B because it requires 4 volts, R4 attached to point C because it requires 2 volts, the dynamics of adding on additional circuitry does change a lot of things and changes things in such a way we can't keep these original ohmic values, and you'll see why in a moment, okay? Let's take a look here. Okay, so we're going to use current analysis. I said current analysis was a very powerful tool, one of 2 very powerful tools that you'll be using for troubleshooting. And we define current analysis as being a method of tracking the movement and the values of currents as they flow through a circuit. I've got the yellow arrows here demonstrating all the different paths for electricity to flow. What current analysis reveals in this particular case is that there's going to be a problem of keeping the original voltage divider resistor values of 1 kilo ohm, 2 kilo ohm, and 2 kilo ohm. So let's take a look at the calculations. If we keep from the previous slide, previous calculation, 1 k ohm, 2 k ohms, and 2 k ohms, and from previous analysis, we had 1 volt across R1, 2 volts across R2, and 2 volts across R2. Those were what was necessary to set up the red voltages at those points with respect to ground. However, if we go to do the math, let's take a look at the values of current. The value of current for R1, the current through R1, is going to be the 1 volt across R1 originally, and the 1 k ohm that we figured would be the appropriate design for the resistance. That calculates to be 1 milliamp, Ohm's law. Ohm's law also then helps us calculate the current through R2. R2's current is calculated as the voltage across R2 divided by the ohms of R2. In this case, it would be 2 volts divided by 2 kilo ohms, and that's also 1 milliamp. R3, IR3, the current through R3, is calculated as VR3, voltage across R3, divided by the ohms of R3. In this case, also 2 volts divided by 2 kilo ohms, also 1 milliamp. All this was hunky-dory, happy as a pig in mud, with 1 milliamp flowing through a simple voltage divider. Once we attach these loads is where we're going to run into a problem. Because if you follow using current analysis, follow this now, watch carefully. Electrons leave the negative plate of voltage source. They flow down to ground, and we said ground can be shown any of a number of places. It is a singular point, and even though we don't connect it with a wire, so as the electricity flows to ground point, there happens to be 3 other ground points that are shown in the schematic. The electrons will flow up through R3. The electrons from the source will also flow up into R4, and the electrons from the voltage source will also flow up into R5. This is the nature of a series parallel circuit where part of the components are in series, part of the components are in parallel. So as we have currents flowing up through R3, 1 milliamp, and a current flowing up through R4, 1 milliamp, where does this 1 milliamp go up through R4? Doesn't it make a left-hand turn? And doesn't this 1 milliamp from R4 and doesn't this 1 milliamp from R3, don't they combine at node C? If they combine, think about this now. If these 2 paths of current come together like 2 tributaries of a river coming together, don't the values add? Doesn't it make sense that this 1 milliamp coming up through R3 and this current coming up through R4, because that was a design requirement, coming into node C, shouldn't these two add to give you 2 milliamps? But what's actually coming out of node C is not 2 milliamps. Something's happening here. So we use current analysis to help us draw in the arrows, and the next step of troubleshooting will advance our understanding. So it says here, looking at the current paths above, can you troubleshoot why keeping the original voltage divider, resistors, and currents along with the new load requirements? Why is this impossible? Put this on pause, think about this, write down what your theory might be. Several different guesses. Write that down in your journal. And when you come back from the pause, let's see what would be the next step in our troubleshooting analysis. Okay, the next step in our troubleshooting analysis, my friends, is we now come to nodal analysis. Nodal analysis analyzes the currents entering and exiting nodes. And we had this as one of the earlier slides in this training video. And so what I have here is a node. It's done in blue. It's a rather big node. And I have 3 currents in red, 2 currents in green. And it says we have, according to the rule says the sum of currents entering any node must, it's capitalized, must, it's absolute, equal the sum of the currents exiting that node. So taking a look at the illustration on the right, I have 3 red paths of current. I have A, B, and D in red, and they are shown with an arrow pointing out of the node. So these are outbound currents. There's a current of 3 milliamps in path A flowing outwards. There's a current of 2 milliamps in path B also flowing outwards. And there's a current path of 7 milliamps in path D also flowing outwards. So the arrows on these 3 are pointing out, and they're colored the same, and we have those individual values of current. Now, there's also 2 additional wires that are attached to the same node. You can have any of a number of wires attached to any node. In this case, I happen to have 6. So let's take a look at the green arrows. The green arrows, the one at 12 o'clock, shows pointing inwards. So this is an inbound current in path C of 2 milliamps. And using the same color, green, I have a path E, and it's also an inbound current as shown by the direction of the arrow, and it happens to be 1 milliamp. There is one remaining path. I've labeled that as X, and I'm using a different color. And if you take a look at the arrow, whoa, the arrow is it pointing in or is it pointing out? It can only be one or the other. It cannot be both. Because the rule says sum of currents entering any node must equal the sum of the currents exiting that node. So with a method that I'm going to show you in a moment, you'll be able to very quickly, very easily determine the direction of current flow in path X. You will be able to determine whether it's inbound or outbound. And not only will you be able to determine the direction, you'll also be able to determine the value of that current. So this is called nodal analysis. It's a very, very powerful tool, along with current analysis, to help us figure out what's going on with this series parallel circuit. So is the current in path X inbound or outbound? What value is it? Put this on pause for a moment. Think about it. Write down what your theory is. Do you guess the path at X is going to be in or out? And what value will it be? All right. After the pause, let's take a look at the solution. Here is the solution using nodal analysis. The solution is, as we know that the sum of the currents entering any node must equal the sum of the currents exiting that node, what you ought to do is to list the values of currents into this chart. Take a look at the chart. I've got 2 columns. One column is labeled inbound currents, The other one is labeled outbound currents. And so I'm just going to fill in the values. So I have path C of 2 milliamps, that's in green, so I put that inbound. I have path E of 1 milliamps in green, and that's also inbound, so it goes in the inbound column. I don't have any more green arrows. I don't have any more inbound arrows. So I have these two values that I put in the inbound column. Now take a look at the outbound column. Currents exiting that node. I have path A of 3 milliamps coming out. So there, I write down 3 milliamps in this column. I then have path B of 2 milliamps, and I write 2 milliamps right below it in the outbound column. And then I also have a path D of 7 milliamps, also out, and I have that in red as 7 milliamps. Once you fill in your known values, you have 5 known values and 1 unknown, this big question mark. 5 known values and 1 unknown. You fill them in according to whether they go in or out. Then what you're going to do is you're going to add them up. If you add the outbound, you discover it's 12 milliamps. If you add the inbound, it's only 3 milliamps. But wait a minute. It can't be just 3, because what's the rule say? The rule says that the sum of what goes in must equal the sum of what comes out. So in other words, if I got 12 milliamps on this side and I only have 3 milliamps on this side, something's wrong. Mystery. Because at the bottom, both sides have to equal each other. The amount of currents coming in, the sum of the currents coming in, have to equal the sum of the currents coming out. So if we calculated 12 milliamps in red, that gives us 12 milliamps in green. That's an absolute must because we can't change the rules of nodal analysis. So if we have 12 milliamps that has to be outbound, isn't there something missing in this area with this big black question mark? What do you think? What value could be missing here? What value can be added in the inbound green numbers to give us the needed 12 milliamps total that are inbound? Think about this. So the missing value in the in column to total 12 milliamps, yes, you guessed it. It must be 9 milliamps. 9 milliamps must be here in this column to add with the 1 milliamp and the 2 milliamps inbound in order to give you a full 12 milliamps of inbound current to balance the 12 milliamps of outbound current, because these two sides in and out through any node must, absolutely must be equal. So that missing current is going to be in which column? Inbound. So therefore, I would change this yellow arrow pointing inwards, and I would change the yellow arrow to green as a solution. And what value is the current on path X? The value must be the missing current of 9 milliamps. Cool. Now let's see what we're going to do with this. Here we go. Pardon me. So nodal analysis reveals something to us. So nodal analysis reveals that we have conflicts that are going to happen at node C and node B. Let's take a look at what happens at node C. So I state here at node C, 1 milliamp coming up through R3. There it is in yellow, 1 milliamp as part of the original circuit design. Adds with the 1 milliamp coming up through R4, because that was a design requirement. And you follow the path of the arrows, what happens at node C? You've got 2 inbound currents and only 1 wire coming out. So that current must be an outbound current, and it must be the sum of the inbound currents. So what is the sum of 1 milliamp coming in from R4 and 1 milliamp coming up from R3? So you know that 1 milliamp plus 1 milliamp must add up to 2 milliamps. Hence, we put the X on the original 1 milliamp. I repeat, read this. At node C, 1 milliamp up R3 resistor adds with the 1 milliamp up from R4 resistor to equal 2 milliamps. going through R2 and is not equal to the original 1 milliamp in the original voltage divider. Let's continue. We have another conflict. According to nodal analysis, we have another conflict at node B. So at node B, check this out. We happen to have, take a look at our inbound and outbound currents. We have an inbound current coming up through R2. It's a new value. It's now 2 milliamps, not 1. It's coming up through R2 going into node B. So this is an inbound 2 milliamps. We also have an inbound 1 milliamp, which was required through design parameter. So 1 milliamp flows up through R5, flows into this wire, and comes into node B. So you have two inbound currents going into node B. One of those currents is 2 milliamps, the other one is 1 milliamp. Well, according to nodal analysis, what's nodal analysis say? Nodal analysis says the sum of currents coming in must equal the sum of currents coming out. Well, hey, there's only one wire, one additional wire attached to node B. So therefore, the current on that wire going in through R1 must be coming out of node B. So the two ins is equal to one out in this case. And the two ins are 1 milliamp plus 2 milliamps. So what's 1 milliamp plus 2 milliamps? We must have 3 milliamps coming out of node B. So IR1 must be 3 milliamps. IR2 must now be 2 milliamps, not the previous 1 milliamp, 1 milliamp. That was part of the original voltage divider circuit. We no longer have a voltage divider circuit. We have a loaded voltage divider circuit, which is now a very nice series parallel circuit. So that being said, the current through R1 is no longer the original 1 milliamp. So here we go. Think about this. Look at this carefully. Looking at the current paths above, can you troubleshoot why keeping the original voltage divider resistors and current values along with the new load requirements is impossible? And you can see through nodal analysis, it is impossible. We cannot keep the original 1 milliamp right here going through R2 because nodal analysis says the new current is going to be 2 milliamps. We cannot keep the original 1 milliamp flowing through R1 because nodal analysis says at node B, 1 milliamp plus this 2 milliamps will equal 3 milliamps coming up out of point B up through R1 and then flowing back to the circuit. That's where our troubleshooting logic leads us so far. So where do we go from here? Here we go. Ta-da! You can determine a new value for R1, R2, and R3 because they can't be the original 1 kilo ohm, 2 kilo ohm, 2 kilo ohm resistors. That's impossible because the currents have changed. So if we read this, the original VR1, VR2, VR3, they do have to remain at 1 volt, 2 volt, and 2 volts. They have to remain those voltages. That can't change. The R value, resistances can change, but the voltages can't. Why? Because the original design required point B to supply 4 volts to the load, R5. And the original voltage divider requirements say we must provide at point C the value of 2 volts to support the load R4. We must have 2 volts at point C in order to support the needs of R4. We must have 4 volts at point B in order to supply the needs for resistor number 5. So that we can't change. So what needs to change in order for us to determine the new values of resistances? Well, nodal analysis gave us new currents. The current through R2 was determined to be the sum of 1 milliamp and 1 milliamp. Nodal analysis said at point B, the 1 milliamp coming in from R4 and the 1 milliamp coming in up through R3 must add to give us 2 milliamps leaving node C coming up through R2. So, and then that in turn flows into node B, where we have 1 milliamp flowing from R5 into node B, and we have a new 2 milliamps flowing up through R2 also into node B. So nodal analysis said the 1 milliamp from the right and the 2 milliamps coming up must add together to give you 3 milliamps through R1. That being said, we can calculate the new ohms with Ohm's law. And with Ohm's law, the new value of R1, isn't it just the voltage across R1 and the new current through R1? So the voltage across R1 is the original 1 volts, but the new current, according to nodal analysis, has to be 3 milliamps. The new resistance R2 is calculated as voltage across R2, which was 2 volts, it still remains 2 volts, and that's going to be divided by a new current, no longer 1 milliamp. It's going to be divided by the new current, which we determined was 2 milliamps. And then the voltage, the ohms, resistance of R3, again, using Ohm's law, must be the voltage across R3, which is 2 volts, and divide by the current of R3, which is 1 milliamp. So do the math here and write down what you calculate the new values for the resistances to be. Okay, and let's go ahead and put this on pause, and I'm going to go into calculator mode with you, and we'll do this together. All right. Okay, so from your journal, you should have written down some of the notes from the previous slide, or as you have the screen paused, you should be able to see the previous slide for the calculation for R1. So if you look at the screen and it shows the value for R1, previous slide, if you had written down the value, the formulas, R1 is equal to the voltage across R1 divided by the new current of IR1. That is, turn on the calculator, 1 divide by 3 milli. So there's your 3 milli equals 333.33 ohms. Hopefully that's what you calculate on your calculator. And the prefixes are very nice, as they're handy. If you're not using this in prefix mode, it's also very easy. A couple extra steps, but it's still very easy. 1 divide by 3. And how do we key in milli on a non-prefix calculator? It would be exp -3. And on other calculators, this would be a 10 power key. So 10 power, change sign, not subtract, change sign, 3. So our display shows us 1 divided by 3, change sign 3. And then if we hit equals, this calculator will show you if there is a prefix, we'll see a prefix. If not, some power of 10. So no prefix, no power of 10. That means this is a solid 333.33 ohms. Hopefully you get the same number. If not, repeat the calculation as I've shown you. Write this value down for the new value of R1. Clear. Okay. So next, what we're going to do is do the calculation for R2. So R2, clear, is going to be 2 volts. And we're going to divide this by 2 milliamps. So 2, shift, there's my milli. And according to my prefix, I get a new resistance, or a resistance of 1 kilo ohm. It wasn't previously 1 kilo ohm, but now under these conditions, it must be 1 kilo ohm. So hopefully you will write that down for the value of R2. Write down R2's value equals to 1 kilo ohm. And hopefully as you've gone through these steps, you should calculate the same. That being said, let's go ahead and do the last one. The last one is R3. So R3 is the voltage across R3, which is again 2 volts. And now we're going to divide by R3's current. R3's current, we determined, was 1 milliamp. So 1, shift. So there's my 1 milli. And then I hit equals. I get 2 kilo ohms. Okay, 2 kilo ohms. So the value of R3 should be 2 kilo ohms. So write that value down in your journal and let's compare and see what we've got. So come here, do this. Oops. Maybe I wasn't sharing. Oops. Share. Let's go here. And let's go here. Okay, so now we should be sharing. So question is, have you calculated the new values of R1, R2, and R3 yet? And if you have, ta-da, yes. This is what we calculated a moment ago together. The new value of R1 is 333.33 ohms, which I now have written into the circuit, the schematic. R2 is 1 kilo ohms, which I now also have written into the schematic. R3 is 2 kilo ohms, which I have in the schematic. So now, as we look at this, we can see all the currents that are flowing, the values of the currents, the directions of the currents, how they meet in the nodes, how they exit the nodes, and everything balances out. So now let's go ahead and do some troubleshooting on the breadboards. So let me go ahead and put this back on pause and switch to camera mode. All right, so in camera mode, we have the voltage divider circuit as we had measured before. We measured the resistances, we measured the voltages, point A, point B, point C to ground, and we measure the voltages across each of the resistors. So not changing anything here because these are the original resistors of the voltage divider. We're just going to double check. This is on voltage mode. Oh, turn the beastie on, that helps. A little bit over 5 volts because my power supply is a little beefier than 5. That's okay. So I get a little bit more than 5. Hope to see 4 volts at point B. I see something pretty close to 4 volts. Hope to see 2 volts at point C and pretty close to 2 volts there. So the voltages at key points are correct. I have the original 1 volt ish across the first resistor, and then 2 volts across R2, and roughly 2 volts across R3. Okay. And hopefully, as you've built your voltage divider circuit same way, you should be able to reiterate these values very quickly. So now I'm going to show you what happens if we attach loads to this. Okay, so in camera mode, let me explain to you what we have. We have the original voltage divider that we just remeasured, 1 volt, 2 volts, and 2 volts, giving us voltage at point A of 5 volts, voltage at point B of 4, voltage at point C of 2, and 0 here. What I have on this board are the loads. So R4 is here. R4 is the 2 kilo ohm. It will have 1 milliamp flowing through it, and it will be attached to point B. I have these two resistors in series with each other. So this is 2K, this is 2K. So the combination for R5 will be 2K plus 2K, giving me the 4K that I needed for R5. And that is attached to point B in order for us to be able to enjoy 4 volts at point B. Now, covered under here is the actual finished circuit, but I don't want it to be distracting to us right now. So I will connect the two boards together the way that the voltage divider is set up. And so for a moment, what I'm going to do, because I'm not using 2 power supplies for this exercise, this will only be 1 power supply controlling both sides of the circuit, the voltage divider side and the load side, R4 and R5. So for me to be able to do this, what I need to do is momentarily, let's pull out the jumper here, park it, pull out this jumper, and park it, pull out this jumper, and park it. I still need to connect the 2 boards together. So what I'm going to do is I'm going to use these jumper wires because I'm going between boards. So I'm going to insert point B. So here is point B over here. And I'm going to attach it to point B where I need it on this side, right there. So if you look at this carefully, point B is the point between R1 and R2. I have 4 volts here originally without any wires attached to it. We measured 4 volts here. We hope to see 4 volts over here, but you'll find that we won't be able to because these load resistors change the balance of the circuit. I now have 2 more jumper wires to put in. I need to put in a jumper wire for point C on this side to go to point C over here. So I will go ahead and put point C over here, top of R4, and then we will attach it to point C over here. So look at this carefully. Point C is the top of R4, and point C is at the point between R2 and R3. We have one more jumper wire we have to do, and that is to complete the bottom part of the circuit, and that is the ground. So this is attached to point D on this side, and we will attach it to point D on this side, which is right there. So looking at this very carefully. Point B is now attached to point B, the top of your R5 resistor, 4K ohms to ground. Point C originally was 2 volts, and 2 volts to point C over here to the top of the R4 resistor, and then the bottom of these 2 loads are attached via this jumper to the bottom of the voltage divider, completing our circuit. So what we have here is the circuit board version of what we've looked at your drawings so far. So now what I'm going to do is make sure this is on voltmeter mode and turn this guy on. And as I've said, we were able to enjoy 4 volts here before at point B. I guarantee you we will not see 4 volts now. And we don't. If we don't have 4 volts at point B now, we don't have 4 volts on this side at point B. No, we don't. It's 3.273. So something's dramatically changed. We previously had 4 volts over here. Sorry, let me move my hand. We previously had 4 volts over here. We now have 3.267. If I momentarily yank this wire, and momentarily yank this wire, get my hands out of the way. Now the jumper wires are not attached. I still have my original over 5 volts. I still have my original approximately 4 volts, and I still have my originally approximately 2 volts. But once I hook up the load resistors here, here, and here, that 4-volt voltage and the 2-volt voltage have now changed. So here we no longer have, oops, wrong part of the circuit, sorry. So here we had previously 4. There's your 3.273. And then at point C, we previously had 2 volts. Yeah, sorry, Charlie, no 2 volts. And this load resistor R4 requires 2 volts. Let's measure on this side. Yeah, it doesn't measure 2 volts. So as we surmised in the slides ahead and our calculations, we knew there was going to be a problem. We couldn't keep the original voltage divider values, original 4 volts and 2 volts here, based on those resistor values, the moment we hooked up our loads. So what we needed to do was to calculate new currents going through R2 and R1, calculate new resistances for R2 and R1, and once we put in the correct value resistances, then we would be able to achieve the voltages and the currents that we hope for. So what that looks like, my friends, is I'm going to go yank this jumper out. yank this one out, yank this one out. And then on this side, yank this out, yank this out, yank this out. Turn off my power supply, detach it, set this aside because the original voltage divider is now useless to us because of the original resistor values. And what I've done underneath here is I've built the circuitry with the new resistances that we had determined would be appropriate. So let me go ahead and put back in the jumper wires to attach circuits properly. So at point C, we put this jumper back in. At point B, we put this jumper back in. And at point D, we put this jumper back in. Right there. All right. So what I still have is a voltage divider. I still have three resistors, R1, R2, and R3, although these are different values now. I still have a point A, point B, point C, point D. I still have an R4 that is attached to point C, requiring 2 volts. We still have an R5 of 4 k ohms, requiring 4 volts, which we hope to see at point B. So now with the new resistor values that we recalculated, all this should work out very nicely. And let's see what happens when we turn everything back on. So I'm going to light this guy up, turn on the multimeter, and now let's see where we stand. So first of all, I'm going to double check my source voltage. We have an excess of 5 volts. I'm going to double check my voltage at point B. So with the original values, that changed from 4 to 3.2 something because we added these load resistances. Let's see if I have, with the new resistances here, am I able to achieve something close to 4 volts at point B? Look at that, 4.14, pretty close. Now at point C, we originally had 2 volts, but once we added the loads, it was way less than 2 volts to something, 1 point something. Now with the appropriate new R1 and the appropriate new R2 changing up the voltage divider sum, we still are able to maintain 2 volts at point C to supply the needs of the R4 resistor. Let's see if we get it. Look at that. We needed 2 volts at point C. We now have 2 volts at point C. We needed 4 volts at point B. We have 4 volts at point B. Voila. So now by recalculating the new values of R1 and R2, inserting them in here, we now have a voltage divider on this side that is now loaded. So this is called a loaded voltage divider that meets all of the circuit parameters. So what you've got is this is a very, very nice series parallel circuit. The series component is right here for the R1. Going back to the voltage source, I have another series part here between these two resistors making up R5. So the total resistance from here to here is my needed 4 volts. So 2K plus 2K gives me 4K between point B and ground. This guy is a 2K ohm resistor. So with 2 volts at point C, 2K ohms, I should be able to have my 1 milliamp. So we should be able to test 1 milliamp through here, which was our original circuit requirement. We should be able to test 1 milliamp through this jumper, which was one of our original circuit requirements. So 4 volts, 1 milliamp. We calculated 4K ohms to make that happen. 2 volts at point C, top of the load. We must have 1 milliamp of current. We calculated an R4 of 2K ohms. And in order to achieve 2 volts here and 4 volts here, we needed to restructure the ohms of R1 and R2. So now let's go ahead and check to see if our currents make sense. Do I have 1 milliamp here? Do I have 1 milliamp here? And then do I have the 1 milliamp here, the 2 milliamp here, and the 3 milliamp here that we had calculated earlier. All right, let's go ahead and check. Switch this over to ammeter mode. Do this very carefully. Don't spin this really fast, as you don't want to wear out the contact points. Make sure this is milliamps, make sure this is DC. We're ready to measure current. And you recall, in order for us to measure current, we needed to break the circuit open and measure current. So the very first current we're going to measure will be the current through R4. We require 2 volts, 1 milliamp. So the way this is structured, it's flowing 2 volts at point C across the resistor to ground. So if I yank this blue jumper, that will create an open at the bottom of my R4 resistor. Watch this carefully. Yank the R4 jumper. I'm just going to park it temporarily someplace. And this is in the ammeter mode. And connect the probes only to the open. Okay, only to the open. Don't want to blow any more fuses. So 1 here and 1 here. Hopefully we see something close to 1 milliamp. Sweet. 1.03 milliamps. Pretty darn good. Now, if I'm going to measure the next current through the R5 branch, R5 load, I have to yank this jumper. But before I yank this jumper, I have to rebuild the jumper here for the R4 resistor. Now yank the R5 resistor jumper, park it for a moment, and we now have an open. The open is from here to ground. So here's one end of the open, here's the other end of the open. Put the red probe, the more positive side of the open, put the black probe in the negative side of the open. We hope to see something close to 1 milliamp. And look at that, 1.04 milliamps. Now, suppose you do something and then you switch it around and you say, hey, I've got a negative 1.04 milliamp. What gives? Where's this negative current coming from? Well, that's because you have your ammeter probes reversed. The red probe must be on the more positive side of the circuit, which is here, and the black probe must be on the more negative side of the open, which is here. And so here we show the 1.04 without the negative symbol. So we were able to verify the current flowing through load number 5. Sweet. Now let's go ahead and rebuild this and measure the current through go park it back. Yep, get back down there. Oops, sorry. Okay. Now we want to measure the current through R3. So here's my R3 resistor. R3 exists between point B and ground, between point C and D. And I happen to have a jumper here placed very conveniently to measure the current from point C through R3. So I'm going to yank this jumper. And by yanking this jumper, I'm going to park it. And I should see 1 milliamp from point C flowing through R3. Let's see if we see something close to 1 milliamp. Look at that, 1.03 milliamps. Sweet. Now let's go ahead and rebuild this. Take this jumper and rebuild it. Now, the current through R2, take a look at R2. R2 is between point C, right here is point C, and between point B. So between B and C, according to our schematic, we had 1 milliamp coming up through R3. We had another 1 milliamp coming up through R4. Don't these two currents combine at node C? 1 milliamp plus this 1 milliamp combined at node C to give us 2 milliamps that's supposed to flow up through R2. So I happen to have a convenient jumper already built in right there. If I yank this jumper, it'll give me an open between point B and the top of R2. That's where I can measure the current that actually flows through R2, and that, if everything goes well, should be something close to 2 milliamps. So let's go ahead, yank this jumper and park it. And now get our probes and measure. here, and here. Do we get something close to 2 milliamps? Lo and behold, look at that. Glory, hallelujah. 2.08 milliamps. Pretty darn close to our desired 2 milliamps. All right. We have one more current to measure, and that's at the top of the circuit. So let me rebuild this guy. So rebuilding this guy, pop this guy back down here, push it down. And the last current we're going to determine is the current that flows up through R1. So take a look at what happens here. We have currents coming up through R3 and R2. 1 milliamp plus 1 milliamp gives us 2 milliamps through R2. The 2 milliamps going through R2 flows into node B. The R5 milliamp, 1 milliamp, comes up through this way to node B. So what happens with nodal analysis at point B? The 1 milliamp, which was required as part of the design, flowing into node B on this side, plus the 2 milliamps we just measured flowing up into node B, nodal analysis says at node B, these two currents must combine. So I have two inbound currents. I must have one outbound current, and the one outbound current must be the sum of these two. So 1 milliamp plus 2 milliamps. We should expect to see 3 milliamps through here. We calculated it. Now we're just going to measure it and confirm that the board is built properly to match our calculations. Yank this guy, park it, and now we have an open at the top of the circuit that will allow me to measure between the red rail right here and the negative side of the open. We expect to see something close to 3 milliamps here. Let's touch here and touch here. Lo and behold, what's our multimeter show us? 3.12 milliamps, only because my power supply is a little beefier than 5 volts. My power supply is outputting 5.12. So yeah, a little bit more than 3 milliamps is perfectly okay. Look at that. So everything in our measurements is making sense with our and matching up with our calculations. And this is what you should be doing hands-on, side by side with me, not just enjoying watching the video, because we learn by doing. This whole sequence of videos is really emphasizing hands-on skills. So unless you take the time to actually build the circuits and make the measurements and do the calculations, you're doing yourself a disservice if you don't do the necessary hands-on steps of the calculations and hands-on steps of circuit building and noodling things out. So if you like this hands-on approach, where we go through theory, we go through, in this case, design, which was new to us, and also analysis using two different very powerful methods, nodal analysis and current analysis, and then refiguring the proper way to rebuild this in order to achieve the design parameters that were required for this particular circuit. If you like that hands-on approach where we've measured everything and confirmed everything, give us a thumbs up. Truly, give us a thumbs up and subscribe to the channel so that when new videos happen, you'll be informed. And we're not done yet because we're going to verify this with the software simulation outputs and see if the software simulator confirms our calculations and also confirms our measurements that we just took. So hold on just one moment and we will go to one more slide. Okay, the last slide goes to show the circuit simulation software. In this case, I'm using TINA, TI. TI stands for Texas Instruments. This is readily available on the internet. It's a great tool. And in a separate training video, I'll show you how to use some of the simulation softwares. But as you can see here, we have the original 5-volt source, but we have the new value of R1, which is 333.33 ohms. We have a new value of R2, which is 1 k ohms. The R3 remained the same at 2 k ohms. R4 was the design required 2 volts with 1 milliamp flowing through it. So R4 we determined should be 2 k ohms. R5 required 4 volts with 1 milliamp flowing through it. So we determined R5 should be 4K ohms. So by popping in our calculated values for these resistances into the simulator, we would be able to see the measurements and that they do in fact jive with what we want. So the current through R4 needed to be 1 milliamp. So look up IR4. So IR4 is right here on this row, and it is 1 milliamp. The current through R5 was required to be 1 milliamp. Take a look at IR5. IR5 is also 1 milliamp. Take a look at the current that flows up through R3. That was 1 milliamp, and IR3 is 1 milliamp. Look at that. So at node C, don't these two currents combine? The 1 milliamp through R4 and the 1 milliamp through R3, don't they add to give us 2 milliamps going through R2? We measured it. So let's see what the simulator shows up. We're looking at IR2. So IR2, lo and behold, 2 milliamps, just like we predicted with our calculations, just like we measured a moment ago using the breadboard. And finally, at node B, which sits between R1 and R2, at node B, we needed to supply R5 with 4 volts, 1 milliamp. That allowed us to calculate the 4K ohms. So if I have 1 milliamp flowing up through R5 into node B, and I have 2 milliamps coming up through R2 into node B, 1 milliamp in, 2 milliamps coming in, how much current must be exiting through R1? So 1 milliamp plus 1 milliamp we determined was 3 milliamps. We calculated it. We measured it. And what does the simulator say for IR1? IR1 is given here as 3 milliamps. Sweet. So all 5 currents on the simulator as the output of analysis jive with our calculations and our board measurements. Now let's take a look at the voltages. The voltage at point 0.1 is the top of the circuit, should be 5 volts across all 3, and it is 5 volts. The voltage at point B is specified in this case as 0.3. 0.3 is point B. We needed 4 volts here across R5, and 0.3, V voltage 0.3 is in fact 4 volts. Cool. The voltage at point C was required to be 2 volts across the R4 resistor. And in the simulator, they assigned 0.2 instead of point B. I can't change these to alpha characters in the simulator, but we know that this top of R4 is point C in our schematic. So this was required to be 2 volts. And what do we have at point C, which is voltage 0.2? Right here, voltage of VP2 is 2 volts. So the currents jive and the point voltages jive. Now let's do one more thing and see if the voltages across each of the voltage divider resistors, do they match? 1 volt here, 2 volt here, and 2 volt here. Take a look at VR1, it's supposed to be 1 volt. Wow, the simulator does also simulate tolerances. In other words, it does also simulate some margin of error given the resistors being 1% or 5%. And so the simulator simulating the margin of error instead of 1 volt gave us 999.99 millivolts. That, my friends, is 1 volt. Take a look at the voltage across R2. We anticipated we needed 2 volts. So VR2 is 2 volts. VR3 was needed to be 2 volts. VR3 is 2 volts. VR2, excuse me, the load resistor number 4 required 2 volts. So VR4 is 2 volts. VR5 load resistor required 4 volts because it was attached to point B. So VR5, take a look at VR5, 4 volts. Spot on. Everything that we had predicted through our calculations, everything that we had measured on the breadboards with our digital multimeter is also confirmed using the circuit simulation software. Hot diggity dog. All right. This completes our voltage excuse me, our troubleshooting of series parallel circuits. This is the part B, and we'll see what comes up next. What else this mad scientist can figure out that'll really stretch your brain cells some. So again, if you appreciate the hands-on approach, you appreciate the sequencing of looking at a circuit and analyzing it, and then building the circuit, and then measuring to make sure the measurements match our calculations. If you, especially in this case, you learn two new skills, the designing and analysis with troubleshooting through nodal analysis and current divider current analysis. If you appreciate all of this, give the video a thumbs up, as well as subscribe. Doesn't cost you anything to subscribe. And if you see the need for any of the supplies, the kit, the power supplies, the multimeter, all of the Amazon affiliate links are in the a narration of the video. So by all means, click on there and acquire what it is that you don't have and what you feel you might need. So with that, thank you so much again. And we will see you for video number 10 coming up. Have a great evening. Bye.